Alright, hello everybody. Welcome to another Angular pull request stream. Today we are gonna look at performance and specifically at one line which I wanted to fix based on what we discovered last stream. And before that, I am going to pull up the browser and look at the previous pull request and address the feedback, which I think it was literally like add the quote marks or something. This one, right? Cool, yeah, so there is like, it says one minor comment. Hey Dan, yes, Angular will become super fast, maybe like 7% faster on one test. But we'll see, if we do like 7% per day, you know, compound interest and stuff. Cool, so, I can just commit suggestion, I think. Commit changes. Boom. I think that's it in terms of reviewing the previous one. Might be done here. Okay, so have inclusive language. That's good. Alright. Oh, so what we are... my mic is far away, yes. Is it much worse? Wait, let me rotate it the right way. Okay, is it oh, here you go. I think it was rotated the wrong way. I think now it should be much better. Let me know if it's better. Cool. So we're gonna fix this thing. One thing I also wanna test is the optimization. So let's see. Okay, don't need the regular expression. They changed the shortcut for this and now I'm confused every time. Here you go. Good at... Now it's good, perfect, thanks a lot Dan. So what I wanna do is this. I wanna see if it will be stripped out. And if yes, yeah. So I want. They have this thing which is which exists because the linter complains. So I think this should work, right? So it says avoid top level property access. In the previous stream, we tried to understand what the issue is here, and I think what we came to was that when running like optimizer, which I think is Terser, it will not optimize it. I don't think it will remove it, but there is a chance it might not optimize it. So Angular uses Terser, I think. Terser. Maybe there is a playground. No. Terser.js. Here you go. Parser, Mangler. So it's kind of an alternative to Uglify.js. So here is the top level something, right? To enable the Mangler, you need to pass Mangler option. Mangler names declared in the top level scope. My internet on your stream was dropped, on which I think was Terser. So we're basically, is it back? I hope it's back. Basically what we're doing is we're looking at at the cursor and looking at mangling, and there is a word top level. Aha, it's your internet. Cool. And I think that's probably related, right? Aha, okay, then it's gonna reboot. I'll let you know if you miss anything interesting. So here is no top level property access. I think it's different. I think this is different optimization. But basically to fix the lint, they had to do this. And my guess is that was not required. One second. Cool. Right, so we've seen that link before. Are able to reduce, check side effects. Sometimes these tools cannot know if a certain piece of code is unused and safe to be removed. The most common case is imported code with side effects. I think I might understand that. Or maybe not. Let's see. So let's say actually, I don't think it applies to this case, but in the case where this function was exported, right? Let's say it's exported. Export. Then what happens is, let's say somebody else is importing, let's say this class is exported. So somebody else is exporting class from this file, but not this function, right? So we know, like, if this function is not important, if it's not used anywhere, then it's safe to drop. But it uses this thing, right? So if we don't include this function, can we also drop this const, which is only used in the function? And the answer is we don't know, because potentially this thing had the side effect. So this this call might do something unrelated to this function, although this thing is only used at the function. So this way it will not be tree shakeable. I think that's how I understand it. And I think that kind of makes sense. So what they're doing is this, which fixes the lint rule, but I don't see how it makes it better tree shakeable. So this is equivalent of function, which has function, right, which has this return, and then we just call this function, right? How does it help? It doesn't, right? We still call this function, and we still can have some kind of side effect from this thing. So it still will not be removed. So I think all this thing is doing is basically like linter shut up. I think it would be a better way to just say like disable tslint or something. Is it tslint? Yeah, just literally like tslint disable, and that's it. Anyway, okay, so what I've been looking at the previous stream was this. Let me see. Character code at DOM renders. There was another place where this was used. Hey Dan. So I think I understand what they like. The very short version is, let's say this function is exported, and let's say this class is exported. So if somewhere else we only include the class but not the function, then we can tree shake this function, no problem. But can we tree shake this thing? We don't know, because we're calling some property of something which may have side effects. So this way the function will be dropped, but this top level thing will actually stay. And then this thing does like whatever they had there, does not fix anything. At least I don't see how it is, and maybe I misunderstood understanding the whole thing. But well, cool. All right, so what I want to do is find another place. This thing. Oh, I see. So I already made the change. But if I do git rollback and rollback this, we'll basically get this thing. So it's a function. It checks if something starts with an @ symbol, which is here. Oh, interesting. So, and the way they check it is, instead of doing name 0, which would give the first symbol, they are only checking the character code, which will be like 64. And what they say in the PR is, let's see, let me annotate this. This simple change speeds up the element text create benchmark by 7%. Right? Which is nice. 7% is nice. So what I'm thinking, if I say name starts with, this should be, and then I can take this thing and take it out. I don't know, add character, and then I just take it out here. This should be even faster and also much easier to read. Okay, that's what I think. And also you don't need this giant comment. And I assume, like before, because there was need to support like older browsers, they did not use starts with. But the question is, can we use it now? And I think yes. I think like if we look for starts with, maybe on a higher level, then there are other places where this is used. So my guess is that that we can do that. And then the other thing I wanted to see is if they have this @ sign thing. Let's see where it's used at all. Just in one place. Do they do similar thing for other things? Like backslash. Yeah, they do. They do, okay, in styling parser. So it seems like this. But here we cannot use starts with. What about underscore? Same thing. Underscore. All right. They have a whole map of those things. Okay, why is there one for 9 and one _9? Let's see. I think, like, okay, this seems like this is a quick way to say a number, and this is a quick way to say like it's a letter, right? Consumes all the characters belonging to style, key, and token. So this is some kind of CSS parser. I think this is for, actually I don't know what it does. Class differ. Returns the index of class to search in class name token. Alright. Anyway. Cool. So it seems like those things are used a lot. And then is it worth to... Yeah, okay, anyway. Let's send the pull request and let's see if people think it's useful or not. Worst case, they Angular reviewers will just say no, and that's also fine. It's cool. So now what I wanna do is... Thank you. Thank you. Alright. So now we can run the perf tests once again. Fish perf. Okay, so I've been doing it on a previous stream. I just want to verify it one more time. I'm probably not gonna run it 60 times like I did before. But here is a number. I can change to 10,000. So I think what they do is they keep running the same thing over and over, and then they measure time. So if for 10,000 runs there was no improvement, I think I understand it now, then it will be like, okay, fine. Alright, so what we're doing here is I just copy pasted a command from the readme right here. So we build the benchmark, and this specific benchmark is element text create. So what it does, it basically creates like a bunch of buttons, and while creating those buttons, what it does, it looks at each property and it checks whether it is an animation prop, which it is if it starts with an add character. So if it does one thing, otherwise it does something else. So we don't really care that much in which context this is run. All we care about is the result of this test. So if this test is faster, I assume like that's a good solid contribution. Another thing I saw in README, but I didn't have a chance to look at, is de-optigating. So it seems like this is where you can see how browsers optimize things. Investigates v8 Node.js. I have no idea how to use this, but there are like people very excited about it, so that should help. There are blog posts. I think we can dig a little bit into the blog post while it is building. I don't know how good of an idea it is to measure performance while OBS is running, but well. We're excited to see recent updates to V8 as a part of blah blah blah. What's the date of it? 2018. So it's not so new. It's not so new, right? But I want to see how they use this deoptigate, if they do. Here you go. So that's article by the actual author of the library, right? It's the Thorsten. So he defined two vector functions, add and subtract, and okay. Summary of files. So here something is happening, right? Wow, that would be interesting. De-optimization. So I assume this is de-optimization because wrong map, but I don't know what it means. Let's see. When executing our script, wanna try? Yeah, I wanna try once I run the second test. Like next thing we're gonna do, or maybe I should run deoptigate now, and then look at the results while the second thing is running, if we can. Let's try. Provide us with, in our case, vector.js. For each file, it shows. Oh, I see. So it's just a table. So it optimized 3 things, and then de-optimized 1 thing. Okay, and then inline cached something. I don't know what inline cache is, but I think I will know very soon. We're provided with the source of the file on the left, with annotations pointing out potential performance problems. Okay. On the right, we can learn more, blah, 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 blah. Clicking on the annotation. Okay, we'll see this very soon. I'm waiting for this in the bottom to be done. At quick glance, we can see that subtract shows no potential issues, but add does. Why? Related de-optimization information on the right. Note that there is a wrong map for eager bailout. It's like a whole different language. Meanwhile, our first perf test is done. So I'll create a scratch file. And then I say test 1 original version. Cool. So it I still not sure what this count and iterations are. All right, so let's try the deoptigate thing, right? So I'll install it. And then, all right, what happened? Rather, the word which might not, if you really meant it, make it explicit by running. I don't know what this means. Can I just go like npx deoptigate? Okay, it's doing something. Meanwhile, I need to copy the name of the benchmark. Element text create, right? Okay. And then problem. Unable to find v8 log. So deoptigate, and then I just paste this thing. Oh no, I copied it twice. All right, let's see if this works. It seems like it's running something. I don't know if we need 10,000 extra runs or whatever, but fine. Cool. So meanwhile, let's see. Something is wrong with the add function. It seems like they do exactly the same thing, right? Except this one adds and the other one subtracts. So what's wrong with why does it not optimize it? Right? Why does it clicking on the blue, checking low severities. Okay, we see that add was optimized after 32 milliseconds. At around 40, it was provided an input type that the optimized code didn't account for. I see. So it's not about what's written here. It's about what's written here. Or somewhere there. Right? Oh, nice. Okay, so we actually have three severity 3 inline cache issues. Files details. Okay. I think I'm just supposed to click on this, right? So I'm interested in the one which has the add character. No? Maybe just 64? Up. I think this thing, right? This is the optimized version of what we're doing. It just inline 64. So it does it with or without this weird self-executing function we looked at the beginning. I don't see anything in this region at all. Any like optimizations, de-optimizations, nothing. It all like ends at line 200 something. Oh. Inline caches. Oh. I watched a talk about this. Megamorphic, monomorphic. I think like monomorphic, it means like there is just one type of data coming, and like megamorphic is different. Or maybe I'm just confused. I'm definitely not an expert. Okay, let's read a little bit more about what happened with the add function. So they iterate over things, and then they just run it. Is this 1000? Yes, 1E3. I'm always confused by this notation. Let's check. 1E3. Yeah, so that's 1000. 1E8 is many 1000. Cool. So for 1000 times, he just runs them with simple numbers. So at this point, the engine optimized the whole thing, and they should be optimized. Now he runs them again, passing objects to add that don't have exact same type as before, since their properties are assigned in a different order. Different order. But how is it different? Oh, really? That's interesting. So this one goes like X, Y, Z, but this one goes at Y, X, Z. and then to subtract, pass the same types of objects as before. So despite the actual structure being the same, it cannot optimize it because the order is different. Yes? Right. When executing our blah blah blah, so you can open it in the browser. I didn't know this matters. Yeah, me neither. This is interesting. So we're jumping in the world of performance optimization here, right? Okay. So they run it, and then they say that this thing is good, but this thing is not good. But only for some reason it only shows it for X. And they're the same kind, it's just the order. Highlights optimization on the right. Note the reason. Okay. In summary, the add function executes via optimized code in the end, but that code needed to handle two types of inputs, different maps, and thus was larger and not as optimal as before. On the contrary, subtract was only optimized once, and we can verify by clicking the green triangle that it's good. Is there green triangle? I didn't see it. Anyway, let's assume it was there. Maybe you have to click on this thing first. Some of you, that's what I want to know, may wonder why a V8 considers the object created via this assignment different from the other one, since they have exactly the same properties assigned in different order. And this is due to the way, oh shit, I want to read it. I don't know if I should do it now. Data times. Ooh, I love this. I'm gonna mark it as like add to reading list, and like on one of the future streams we'll check it out. Anyway, so let's for now let's skip this. JavaScript objects are initialized and is a topic for another post. Okay, I will also explain this in more detail as part of my talk at Node Summit. We can check it out. I can also ping Torsten and maybe we can ask him questions or something. By the way, we have Artalar coming next Thursday to talk about state management solutions in Russian. So that will be interesting. So this does not answer the question of why it's so damn fast. Just shows, or maybe we skip those parts. Anyway, where is the link? Here. Oh no. 1 second. Cool. All right, so while it does, I'm looking at that. I wanna run one more time the same benchmark and see where we get. Oh, so this is also Torsten. Object read some surprising properties of properties. Object is a collection of properties. Property names are always string, yes. That is not string is stringified by toString, yes. Arrays in JavaScript are just objects with magic length property. Okay. I kinda knew that before, but now I kinda need to rethink it a little bit. Hash tables used for difficult objects, aka objects in dictionary mode. Accessing hash table property is much slower than accessing a field at a known offset. I think I kind of started from the from the middle, right? Above shows most common optimized representation. Most objects contain all their properties in a single block of memory. Okay, object, map, extra properties, element, property foo, property bar, property poo. What's going on here? I assume this represents something. So for some reason, those foo and bar properties are considered easy, but poo and buzz are considered to be not easy. Is it because the value? Named properties that don't fit are stored in Overflow Array. Number properties are stored in a separate contagious array. Okay. So this thing just has numbers. Yeah, this is confusing. Okay, fine. So for now, let me run one more time, and then I'll go get some water. I'll be right back. Alright, I'm back. Because we're running for the third time, and then I consider it to be done. What happened to the optigate thing I was looking at? Okay, can I just do open? Here we go. Okay, back here. Cool. Let's look at severity 3. Let's see what's going on there. De-optimizations. Inline caches. So here is a red phone. Old state initialized, monomorphic, and it's megamorphic. Okay. Tag set. Let's see, maybe there is a comment explaining what this function does. Tag set. No, right? So it's not even a set. So it basically creates an object with the keys of tags. Okay. Cool. So now at least I can understand what it does. And then it sets, so from what I've seen, it's always strings, right? I don't think at any point we have anything which is not string. So in my head, this should be optimized all right. So now let's see what's monomorphic versus polymorphic versus megamorphic. Morphic. Maybe we have some other hints. All right, so this, what's the number is here? 2360. That's even better. Those are like such different numbers. I kind of feel like I have to run it again. Cool. So it's time to figure out the. Somebody explained that to me. Inline caching. Yeah, here you go. Optimization technique employed by some language runtime and first developed by Smalltalk. That's nice. The goal of inline caching is to speed up runtime method binding by remembering the results of previous method lookup directly at the call site. I guess this is for pure functions. Line 395 has a green marker, by the way. Let's check it out. 395. I see a blue one. This is optimizable. So I think optimizable, I would assume it means like no side effects, right? And then I'm looking at this thing, right? Which monomorphic, megamorphic thing. Yes, it's blue. I have a good friend who is colorblind, and every time we do something, he's like, and there are like colors involved, he's like so confused, and it's mind-blowing like how often this happens. He would like ask me, okay, is this red or is this green? Cool. So I think this seems like this is kind of like Memo from React, or like Mois, but on the function on the runtime level, or no? Megamorphic. If runtime uses both monomorphic and polymorphic, then in the ready state be. What? I'm confused. This function always accepts strings and the blue marker confirms it. Got it. Makes sense. Makes sense. So what happens if all of them are strings? What happens here? It always sets this thing to true, right? Always. So why would it be different? Oh, just because of the cast? But why are like, I mean, but this is what optimizer does with trues, and it seems like it's so maybe okay, how about this? This seems create view is optimizable, but this thing here is fine. I don't think that's the problem. Okay. We don't know what functions were called. Also, they should be called more than one time to have old value and new value. Yes. Oh, so you think that's mostly because they were not called... but then why does it need the optimized flag? Okay, so this 2.8... Cool. Let's go back and let's use... Let's use my fix. And now we just run the same thing another time. Cool. Okay, for now maybe this is because of this, but then what's happening here? It seems like everything which comes here, yeah, this is some runtime optimization. Yes. I think we have to Google this megamorphic, monomorphic, polymorphic, or maybe Wikipedia. We just need to pause a little bit and understand it. Okay, so in call site frequently sees different types of object. Performance benefits of inline caching can easily be nullified by the overhead induced by the frequent changes in state of the call site. The following example constitutes a worst case scenario for monomorphic inline caching. So we have like one number string, so this is bad, right? Again, the method toString is involved on an object whose type is not known in advance. Most importantly, that's actually a JavaScript example, right? Looks like JavaScript. The type of the object changes with every iteration of the surrounding loop. An if implementation of monomorphic inline caching would therefore constantly cycle through the initialized and monomorphic state. In order to prevent this from happening, most implementations of monomorphic inline caching support a third state, often referred to as megamorphic state. The state is entered when a particular call site has seen a predetermined number of different types. Can we... Maybe we can just console log this and see what's going on there. Once a call site has entered a megamorphic state, it will behave just as it did in the initialized state, with the exception that it will not enter the monomorphic state ever again. Oh. We may need someone to help us with that. The following. So let's do from the beginning. Cool. So this does not seem faster. It used to be faster for me, but not anymore. Test 2 faster version. And just to verify that we're in the right place, I'm just gonna throw something and see if it breaks it. The following ECMAScript function receives an object, invokes the toString method, and displays the result on the page. Okay. Since the type of the object is not specified, and because of potential method overloading, it's impossible to decide ahead of time which concrete implementation of toString method is gonna be invoked. Okay. Instead, a dynamic lookup has to be performed at runtime. In runtime that do not employ some form of caching, this lookup is performed every time as a method is invoked. But because methods may be defined several steps down the inheritance chain, a dynamic lookup can be an expensive operation. Okay. To achieve better performance, many languages employ some form of non-inline caching, where results of a limited number of method lookups are stored in an associative data structure. Okay. I still don't understand what they cache. So it gets the error. Alright, let's run tests again. Interesting. So before it seemed like it was faster, but now maybe it's not faster. Concept of inline caching is based on empirical observation that objects that occur at particular call site are often of the same type. Okay. In those cases, performance can be increased greatly by storing result of method lookup. So it's the actual two-string method for, let's say, number, right? To facilitate this process, call sites are assigned different states. Initially, a call site is considered to be uninitialized. Once the language runtime reaches a particular uninitialized call state, it performs dynamic lookup and changes its state to monomorphic. Right, so let's say you look up for a string, wasn't there, so now it's monomorphic for string. If the language runtime reaches the same call site again, it retrieves the callee from it and invokes it directly without performing any lookups. Okay, so if the string comes again, we know what to use. To account for possibility that objects of different types may occur at the same call site, the language runtime also has to insert guard conditions into the code. Most commonly, to better exploit branch prediction, say space. If a call site that is in the monomorphic state encounters a type others that one it expects, it has to change back to an initialized state. Okay, I think I understand so far. Okay. The canonical implementation is a register load of a constant followed by a call instruction. Alright. Okay. So it's polymorphic. To better deal with call sites that frequently see a limited number. So if it keeps going with like string number, then we can have a cache of two types. Right? Some languages employ a technique. Once a call site that is in its monomorphic state sees its second type, rather than reverting to an initialized state, it switches to a new state called polymorphic. So that decides on which of a limited set of known methods to invoke based on the types that it's currently presented with. So it's like inline caching, but for few things, like not just for one thing, but for 2 to n, right? Because every call site in a program can potentially see every type in the system, there is an upper bound to how many lookup results are recorded, because every call site can potentially see. So at some point, the benefits of having this cache kind of go away once there are like too many types. And once we get there, it becomes megamorphic. And there is no more inline caching is performed. Okay. Is a jump. Once it reaches maximum size. Okay, I think I understand this. So megamorphic is like after a certain number of types which came through, then it's steady state. So how about we just Google this megamorphic. Metamorphic. Inline caching. Uh-huh. Two 574. This is not faster, right? Let's do it again. This looks the same basically. Which is interesting because it was like much faster before. Right. One type good, two type bad. Shout to me is a request to explain what monomorphism actually means, how polymorphism arises, and why it's bad. Yes, polymorphism is overloaded. That's true. For simplicity, this post will most likely concentrate on simplest property access in JavaScript. At the same time, it's important to understand that everything we're going to talk about applies to any dynamically bound operation. Imagine for a moment that you're interviewing for a great position at whatever, and your interviewer asks you to design and implement property lookup for a JavaScript virtual machine. What would be the simplest and most straightforward answer to this question? Obviously, you cannot go any simpler. Okay. Okay. I actually have no idea what's here. Okay, so I guess this is some stack-based parser. We get property name, we get receiver, and then we put back the result, where we call this get thing with property name and receiver. I don't know what receiver is. Okay, that goes pretty deep. 2.9. This is not faster. Not like last time. So if it's not faster, we're not doing a pull request. Who is Vyacheslav Yegorov? I need to start him somewhere. Alright, I'll just... Oh, I'm already following him. Easy. Oh, he's compiling compilers at Google. It's good. Cool. I have no idea what's going on here, but let's see where he's going. Every time it does a property lookup, it has to execute a generic property lookup algorithm. It does not learn anything from previous attempts and has to pay full price again and again. And that's why VMs implement property lookup in a different way. What if each property access in our program was capable of learning from objects that it saw before and apply this knowledge to similar objects? Potentially it would allow us to save a lot of time by avoiding costly generic lookup algorithm. This I wish it explained why lookup is hard. Okay, so we have an object with property X. We need some help. Okay, so there is like some, I guess this is because it goes over like prototypes and stuff, or I don't know. I don't know why property lookup is expensive. Oh, maybe it's because of that thing we saw before where it they're like simple properties to store, more advanced property to store, and if the object has the same structure, then you can just say go to like this address in memory relative to the start of the object or something. And this is why if you switch X and like some next property, this address changes and you cannot do it anymore, right? So we know that it's costly. There are like lots of assumptions here, so I guess it's not an entry-level article. It's costly to figure out where the given property is inside an arbitrary object. Why? So we would like to do this lookup once and then put the path to this property into the cache. Using object's shape, that's what we saw before, as a key. Next time we see an object with the same shape, we can just get the path from the cache instead of computing it from scratch. Cool. It's called inline caching, and maybe there is like a boom, 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 boom. Cool. Okay, so that's again not much faster. I have a thing for virtual machines, which are implemented in a language they are built to execute. JavaScript VM written in JavaScript. Okay, good luck with that. It sounds like fun. Actually, this would not be. All right. So somebody is writing a virtual machine for JavaScript in JavaScript. That's a star right away. I have another dream connected to meta-circular virtual machines. I have no idea what it is. I want to help JavaScript developers understand how JS engines work. Please do. I think understanding the tools, blah, blah, blah. The more people would stop seeing JS VM as mysterious black box, blah, 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 blah. So there are lots of people who do that. Sometimes I wrap things I know about V8 into hard to digest list of do this, not that recommendations. Right, that's Meta I don't care about. He gave a talk. Imagine that you want to implement JavaScript VM for a language which is similar to JavaScript in terms of semantics, but has a much simpler object model. Instead of just objects, it has tables mapping keys of any types to values. Let's think about Lua. Okay. Cool, so today this actually is slower. Let me undo that and run again. Maybe deOptigate made my laptop slow or something. Cool. What's going on here? Have a checking results computed. So it worked with the throw-in code. No, it threw. So it threw, and basically I went back and removed throw. It got broken properly. Good, but does not help to understand how VMs work. So let's think how it could look like if we had quasi-low written in JavaScript. Is this just copy-pasted code from above? I think so. Oh, I'm pretty sure it failed at some point. Here. So here you see like it threw LOL. And I was like, okay, then I know I'm fixing the right thing. Okay, so there is like table something. What's the table thing? I see. So now, before they were using an object, right? But in JavaScript, they use some table thing, which I assume is how objects are represented, right? So this table thing has a load and store. Okay. And it just has map inside, right? Using Harmony map. Harmony, that sounds like an old article. Yes, it's 2012. Okay. Wow, so, okay. Because potentially table can contain any key, not just string ones. Fine. Now our, wait, what, let's see. So const a equals new map. Is it put, add, set? So what does it mean, any key? Does it mean that you can do this? Oh, I see. So it differentiates them by types, but not. But we need weak map only for references. Okay, I got it. Now our translated code works, but it's very slow because of all those levels of abstractions. And now it's time for inline caching. Let's try to reduce the very same fundamental optimization that most JavaScript VMs apply these days, inline caching. Even JS VM written in Java will eventually use it because invoked dynamic is essentially what? Okay. Oh, I see. So Java does this too, I guess. And it was developed 40 years ago for Smalltalk VMs. The idea is very simple. We want to create a bypass that would allow us to quickly load object's property. If our assumptions about object and its properties are correct, it's hard to formulate any meaningful assumption about layout, blah 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 blah. Okay. Discovering hidden structure. Oh yeah, okay, so this goes very deep. I don't know if I wanna go through it now. Let's look again. So it was in a state of uninitialized and it went to monomorphic. And then article, what's this address in article? So for the key address, it was uninitialized, but then became monomorphic. This thing. And then for the key of article, it became from monomorphic, it became megamorphic. Although all we're setting is this, right? That's confusing. Okay, how about this? We 2920. Let's run again. So I'll create where I can create. I just create a test file. LOL. With this for const keys equals repeat times all right, so we have is 1000 enough? Let's do 10,000 for const key of keys tag set. Actually, for I from 0 to 1000, and then like say tag set, and then here we just use this. And then that can be just 50 split join. Okay, I think that should be it. So now I can go with the px deoptigate and then I can paste here. Let's see if it works. Okay. Okay. Так, alright, so what if I just change it to true? Why don't they just use set? Wouldn't it be faster? Let's see. Okay, so at least we'll know if it's so no, it's not true. Okay, so let's what can we do here? Let's get rid of split here. Tags, and so we can drop join here. What about this? Okay. What if it goes like undefined? Same, right? Try string. Same. How about to just do I don't know if it will yeah, same thing, right? Okay, what about this? What if we had a thing with this okay. So it is just the fact that how about this? If we have something, the fact that res is changing its shape. Ah, yes, I think so. What? Okay, so if we had this, Okay. That's weird. Now it's just empty. Close other tabs. Look at the logs. Yes, missing something at the arguments list. Yeah, good call. Where is this? Split. This? Yeah, I don't think it should be opening the file then. Okay. A. What? So it's already A. And it's writing A. And somehow it de-optimizes it. It's weird. Okay, let me get another run. Okay, so it seems like starts with doesn't bring that much of an optimization as it looked like it does last time. Fine. Wait, so this has an object of a shape of a boolean, and then what we do is we just set this whole thing. So it doesn't change the shape here, but it still complains for some reason. Let me run it again. Okay. So if I just drop the loop, then it should be fine, right? Let's see. Inline caches. Let's see. Alright, so what if we do for I from 0 to 1000, and then we just do this. This doesn't change the shape of the object, right? So why does it complain? Now there's just like nothing. Okay, tags I. Let's do that. Tags length. Alright. What's this? Low severities. Okay. I don't know. I kind of give up here. Fine, I don't know what else to try, it just doesn't make sense. Maybe we can ask Thurston or Vyacheslav. Or maybe I should just read the article. Okay, 2951. Okay, so it seems like it's not faster, right? Seems like it's not worth the effort. 2, 3, like it never even got that fast. What happens if I just inline the add character? Like, will it change anything? Okay, it seems like I'm slowly starting to understand inline cache. Taking down, okay. Ah, I see. So V8 generates a log. V8 log. V8 log. Log. How do I... I don't see any logs. So I guess it just doesn't generate it or just removes it immediately. Definitely need to start this. Cool, let's see how this thing is doing. Kind of feel like this doesn't have to be a large value. I can just bring it back to 500 and make it like very fast. Let's see how quicker that would be. Correct spelling of inline caches, okay. Uh-oh. That looks broken. That looks broken. Node source. Will this work? That page went missing, never mind. Fine, okay. Okay, so now we get different numbers. We get 3188. Three one nine nine. 3155. That actually looks pretty consistent. Now I go and undo this. Alright, now we should get quicker results. Oh yeah, but it will take some time to build anyway, right? Cool. I don't know what happened to node source GitHub IO though. Node source is guess it's node for Linux. Okay, 2925, that's faster. Three one zero six. 3106. That's consistent. And two 667. This is not very useful. 2565. Two 603. It seems like we're getting like mixed results, right? Okay, so waiting for this to run. Alright, so build is done. 3. Okay, let's see now. So if it consistently goes over 3, then it is slower. 3163. 3. Oh yeah, that's much slower. 3162. Cool. Okay, so I guess I don't know why it looked like it was faster last time, but I guess it's actually slower. So I don't think we are gonna send this optimization. One thing I just want to do const here. I don't know if to change anything. I would assume not, but easy to verify. Oh yeah, one thing we can do is, which we haven't tried, is profiling this thing. right? 2923. There's not much difference. Two nine three nine. Okay, so this is not faster. So fine, I can quickly profile it just to confirm. Okay, here, right? Chrome inspect DevTools for Node. Here you go. Okay. So what's this number? 12. Oh, I guess because we're using profiler, it's slower, right? Okay. So I should have started the actual profiler. Okay, let's do now. Okay. Sources profiler. What's this? Heap size change trend over the last 2 minutes, but it hasn't even run yet. Okay, let's do start. Okay. Oh, interesting. So when I hit start, it immediately starts the thing. Cool. And now here, oh no, it still says recording, right? Why is it still recording? Just stop this thing. Now maybe we can search for that method there, can we? Is animation prop. Oh, it's not there, right? We cannot even like, because it's inlined, it will record till you stop. Let's stop. Yeah, so because that thing is basically inlined, there is not much we can profile here. Yeah, and I cannot jump anywhere because I stopped. All right. Anyway. So I guess we're not making a pull request, but we did learn something about inline caching and stuff. Do I want to do anything else, or should I be done for the day? I want to see the... I want to glance through the data types, and I want to see what this repository is, and then I think it should be done. All right. Nodes and resources related to V8 and node performance. Yeah, there is this new table of contents from GitHub, so this is kind of not needed anymore. Hey Georgina. How is everything? Garbage collector. Memory profiling, inspection, snapshots, and code caching. Runtime functions. Enter into C++ functions, accessible from JavaScript. Whoa. Okay, I'll just look at data types. That's what I care about. The data types document explains what data types, blah blah blah. Compiler. Oh, should jump in. Oh, so somebody else started this thing. And here there is no table of content, only for the main review thing. There are some kind of slides. Nope.
So,
So it's a talk from Google. Yeah. Oh, hi. Hi. Who woke up?
because we don't have a lot of type information in JavaScript, we have this dilemma. We want to be able to generate code that can handle all possible different values, all different possible types. But you want to be able to have an efficient representation of numbers. And how do we do this? Well, we use a technique called tagging. So inside a V8, we pass around values as 32-bit numbers and objects.
What? Okay, let's do it again.
Possible types. But
Maybe I shouldn't have sped this up.
you want to be able to have an efficient representation of numbers.
Okay, you want to have efficient representation of numbers. Fine.
And how do we do this? Well,
How?
we use a technique called tagging.
Okay.
So inside a V8, we pass around values as 32-bit numbers and objects, but we
Okay.
want to be able to use the same 32 bits to represent both.
Okay.
And that way, we can have one code path that can handle, in many cases, the objects and integers.
What?
So what we do is we use the bottom bit in each of the values to have a special meaning. If the bit is set, it's an object pointer. If it's clear, it's what we call a small integer, or a SMI. And that's a 31 bits.
But this is from 2012. We don't even know how up to date this is.
Signed integer. Now, if you have a numeric value that you're passing around, assigning to a member, that is bigger.
But also, at least I think it will be easier to comprehend than whatever new optimized version does.
A numeric value that's bigger than 31 signed bits, then it doesn't fit in one of these smiles.
No, it doesn't.
And we have to create what's called a box for it. We box the number,
Okay.
we turn it into a double, and we create a new object to put that number inside of it. And what
Okay.
follows from that is the next speed trap to avoid, which is make sure, whenever possible, you use 31-bit signed numbers for performance critical
Now I know why Chrome ate so much memory, at least in
calculations.
2012.
Because if you exceed 31
Well, how many numbers you have are larger than 31 bit?
signed bits, we will have to convert it to a double value. Now, there's some optimizations that we have that doesn't make it as bad as it seems, but there are cases where that process causes an allocation, and that means that some mathematical operations can cause allocation. The next thing I'd like to talk about is arrays. This brings some of the elements together of the previous two sections. In JavaScript, you can have very large arrays, and you can have arrays that are sparse, that don't have every element inside of them. Yeah? And so V8 actually has two different methods to handle two different types of arrays. The first one is fast elements. And fast elements, they have a linear storage buffer.
Linear storage buffer. Okay, I think that's literally spaced out in memory addresses, right?
And V8 uses them if the set of keys for the array is very compact.
Okay.
If that's
What is very compact?
not the case, so you have a very sparse array, then it uses a different.
Oh, so compact is 0, 1 to 5?
different format, which is dictionary elements. Fast elements, linear buffer, very fast and efficient to access. Dictionary elements, it's a hash table, much more compact, but also more expensive at runtime to access.
All right.
Kind of obvious here. If you want to have your arrays be very fast,
Am I going to make a PR in V8? I mean, right now we spend like 40 minutes being confused about inline caching, so it might be a bit early for PR in V8. But yeah, we looked at this thing called dOptigate, which basically shows which optimizations V8 applies to the code you run, and that led us in whole different rabbit hole of trying to figure out how data structures are stored in JavaScript. So now we're looking at that, but this is like very basic level, and we're looking at like talk from 2012. So if we can travel back in time, maybe I can contribute some optimizations. Now that I'm an inline caching expert as of 40 minutes, but probably not yet.
Make sure that V8 uses fast elements to represent them. And the way to do this is to make sure that your keys start at 0 and that they're contiguous.
Okay.
So don't create an array and start using index number 25,000.
Okay, then you're
Start
screwed.
at 0 and go up.
Oh, that's now I understand when people say that arrays are objects. Because before, like I heard this before, but like it didn't make much sense to me. But for now, I think it makes sense. So based on how you use your keys, arrays are literally object, because in language like Java, when you would want to use an array, you would say, give me an array of X elements, and then it's like very clear how to store it in memory. But in JavaScript, if you start using something with a key of 25,000, then it immediately becomes a hash map or hash, whatever they use, a key object.
Also, don't allocate really large arrays that you're not going to use everything in, right? So if you allocate an array with 65,000 elements and you only use the first 5, V8 thinks, well, that's a very sparse array, yeah? And we'll switch it to dictionary mode, which means the access of the elements will be slower. Don't delete elements inside of arrays. Same principle
Why?
here. Because when you delete elements, it makes the key set sparse, and it can lead to V8 switching the elements to dictionary mode. Don't load from uninitialized or deleted elements. This is an important one. It's easy to get wrong. Here's an example.
Okay. So this is uninitialized. It's initialized. But this is a read, not a write.
Your code will work. You won't notice, and it won't make a difference in the output. However, it will make things a lot slower. So here's an example of doing exactly this. I have a loop here that accesses an array, and it uses the or equals operator, which means it takes the existing value in the array, ORs it with something, and then writes it back. But the first time that you do that, you're accessing an empty array. And when you do that, the JavaScript spec says that's an undefined value. But that's okay.
Yes.
It can be converted to 0, and it's exactly what it does here. Converts that to 0 to do the or equals, and then stores it back in. But that process of conversion means that this operation has to do more checking, and it's more expensive. And by simply initializing the value before you use it, that's the second example here, you can make your code, in this case, about twice as fast.
That seems like a very minor optimization.
So what about arrays of doubles? Remember, I talked about tagging, that we have to wrap double numbers inside of special objects.
Right.
So if you have an array of them, doesn't that make it expensive? Because each element has to have this wrapper object to store the double value. Well, there's a trick that we can use there too as well. So we have a mechanism called unboxing. When you unbox a double, you take the 64-bit IEEE number inside of this double object, and you take it out, and you put it into a linear buffer. So what we can do is track in the hidden class of an array the types of elements that are contained in the array. And if the array contains only double values, it becomes unboxed.
Wow,
What that
smart.
means is that it takes all of those numbers out of the heap objects, out of the wrapper objects, and lays them out in a linear buffer of doubles. But again, it's only if there are double numbers inside of the array. This causes a hidden class change. Generally, that's good, because if you convert the double numbers into a flat buffer, if you have an array of doubles and it's in a flat representation, it's very efficient to access that. And when you store into it, it doesn't require any allocation. But you must be aware that converting between the array that's boxed and unboxed has a cost, and it changes the hidden class. And careless manipulation of arrays can lead to a lot of extra work through this boxing and
Probably not the problem I'm going to have at any point, but that's interesting.
unboxed. I'll give you an example of that. Here's a pretty simple snippet of code. I create a new array, and I assign a bunch of values to the first couple of elements. Looks like there's not a whole lot of work to do here. But because I created an empty array, the initial object that I have, you'll see, doesn't actually have any elements at all because it's empty. So the hidden class says, hey, I'm an array, and I'm optimistically going to assume that I'm only going to assume it contains my values, and that I'm not going to have any deletes, no holes.
Right.
We could do that because the array's empty, so it's actually a true statement. It only has smiles because it has nothing in it. What happens when we assign to the first element of the array, because we didn't have a backing store for the elements yet, we have to allocate it. And by default, we allocate a buffer that has room for 4 elements.
Okay.
Now that the backing store is actually there, we can store the first element in here. And again, this is stored as a SMI, as one of these compact 31-bit signed integers. And now that we have space, we can also assign the second element, also not a problem.
Okay.
However,
That's a
the
double.
next assignment assigns a double value.
Okay.
And what this does is forces V8 to convert the format of the backing store, because we can't store a double array directly in a double value directly into the array. But what we could do is we could convert the existing integer values to doubles, and then with the unboxed version of this array, we could store the 0.5 value. And that's exactly what V8 does. It reallocates a new buffer. This time, each of the element slots is 64 bits. It converts the existing small integer.
Wait, but why not use this format he showed in the beginning with the first bit signifying like if it's integer or double? Oh, I guess because it's an array, right? Oh, because you have... Oh, okay.
Into double values, and then it assigns the 0.5 to the third element. You'll also notice that a hidden class change happens here, because what we did is added a double value. So it's no longer true that the array only has smiles. We now have doubles in there. That means that the hidden class has to be changed. It causes a hidden class change.
Okay. I didn't know about hidden class and what that is, but fine. Okay.
Something similar happens when we try to assign true. So true, there are certain objects in JavaScript which are kind of oddballs. We actually call them oddballs. True, undefined, null. They are not really objects, but they kind of act like objects, but they're certainly not numbers. So when I assign true to the third element, or the fourth element here, it causes another allocation because we can no longer represent this new value in this unboxed double array. So we have to convert it back into its tagged format, which means converting the elements that can be represented as smiles back into smiles. It means reboxing the double value.
Oh.
And now we have a backing store that we can actually store the true value in.
That's interesting. So during this thing, it converted it 2 times to different things.
That's a lot of work. This is a very short piece of code, but we did.
I want like this example to go to like the whole 40-minute talk. So he would insert more values and remove more values, but probably not happening because it's IO and it's not their format. Okay.
Did 4 allocations, 2 array. 2 hidden class changes for just a couple lines of code. There is a better way. If you use an array literal, this is a hint to V8 up front what the values are going to be inside of the array.
Nice.
And given this example here, we have a single allocation. All of this can be done in one allocation. The correct backing store format can be selected at compile time. And we don't have all of these conversions in the initialization of the array. So, touched on this already. Speed trap. Make sure, wherever possible, you initialize arrays with array literals, especially for fixed size small arrays. Also for small arrays, make sure to pre-allocate them before you use them. Now, again, this is different than large arrays. Large arrays, remember, more than 65,000 elements. You want to make sure to grow as you go so that you don't go into dictionary mode. For small arrays, even if they're not completely filled, even if they're small, if they're sparse. If they're small, V8 will use fast elements for them. But only if you allocate the correct size will you be able to avoid allocations when you go from an empty array and store the first element. Don't store non-numeric values in numeric arrays. So if you have an array of double values, V8 can generate very good code for manipulating those values, for those double values. But if you put an object into the array, we have to box everything again, and the code that we generate is a lot less efficient. OK, we've talked about hidden classes and how they are an important piece of optimizing code. Let's actually talk about how we generate code in V8. And this will maybe help you understand a little bit better why it's important to make sure that you understand the hidden classes.
OK.
So V8 has two compilers. The first one is called the full compiler because it can actually implement the full set of JavaScript features.
Good code for any JavaScript.
It generates good code, but not great code. There's an optimized compiler, which I'll talk about later, which produces much better code for most of the language.
That must have changed like 16 times since then.
The goal of the full compiler is to generate code quickly. I talked about before the fact that any time you spend compiling code is added to your execution time. So the full compiler's strategy is to get executing code as quickly as possible. It generates code that is just good enough. But because of that, it basically doesn't do any type analysis. It doesn't know anything about types. And the way that it solves the problem of, and what inline caches do, is they gather type information at runtime, and they optimize the code as you go. So you pay as you go. And here's the way inline caches work. An inline cache, or an IC, is a type-dependent small chunk of code that knows how to do an operation given specific hidden class inputs of a particular hidden class.
But how many things are type-specific? Like I understand toString is, but like why are other things type-specific?
And what they do is they validate the type assumptions. They get a couple arguments in, they check to see if the hidden classes are as they expect, and if they are, then they know that the code that is in the IC is the optimal code for implementing that operation. If not, something has to happen. A new IC has to be generated that can handle the new type information. And at runtime, if different types are seen than what are expected, then through backpatching, the code is changed to use new specialized code for the new
backpatching
types that
okay.
I'll give you an
I don't
example
know
of how
what
it
it
works.
is.
Here's a fragment from the code example at the beginning, the prime number generator. I'd like to take a particular fragment of code there, which takes.
Oh, I think I missed the beginning. Should we go back? Yeah, maybe to have more context, it would be nice.
Need the smaller fonts in some of the code slides later. I'd like to talk to you today about optimizing the performance of your web application. Now, this can mean a lot of different things to a lot of different people. This could mean optimizing your WebGL code to get more frames per second in a game. This could mean reducing the number of network round trips in a client-server application. But what I'd like to talk to you about today is raw JavaScript execution performance with V8, the JavaScript engine inside Chrome. The V8 project has recently moved to the development center, the Google Development Center in Munich, Germany. And as you may know, Germany is the home of the Autobahn. And what you may not know is the Autobahn is not actually a single stretch of road from Hamburg to Munich that runs straight through the middle of the country, but rather it's a network of road. And these days, most of the Autobahn actually has a speed limit, but there are still a few stretches of the road that don't have any speed limit whatsoever. And you can go as fast as you want, as fast as you can. And so, as a resident of Munich and a resident of Germany, I feel especially qualified to speak about moving at speeds that would get you ticketed here in the United States. You might ask the question, who cares about performance? JavaScript performance is fast enough. This is something that only game developers need to worry about, or the developers of highly interactive applications. But I'm here to tell you that you should care about performance. Everybody who develops a web application should care about performance. And the reason is that JavaScript performance matters. It still matters.
Right.
It's not just about making your current application run faster. It's about enabling things that you have never been able to do in the past. Every cycle that you win back when you do performance optimization, you can invest. It's about enabling.
Imagine how just minifiers can make your perfectly optimized source code totally unoptimized.
A few feet away. I think it's interesting.
Yeah, that's a trade-off, right? But I don't think it changed. Like I don't think the optimizers change this. The minifiers change the substance of the code. They actually make sure that what the code does stays the same. So I don't think they can break any optimizations. But at least I cannot come up with a good example of how that could happen.
That in the same place, giving a slightly different perspective, you can have a completely different view of the world. So let's talk about breaking the speed limit today. I'd like to use a checklist as the basis of how the checklist is to make sure you are prepared before this is the one that you have. How a system works. That's actually, I'm not very good at it, but I have a friend I like. And we were 2 rope lengths from the top, from the summit. We were almost there. And I was belaying Michael. I was making sure that if he were to fall, that I would catch him. And he was leading ahead. And he climbed ahead of me around a corner, out of sight. And I heard him struggling with a particularly tricky climbing problem. And then I heard 2 sounds that I will never forget in my life. And the first one was the percussive sound of a rock coming loose. And the second sound was the sickening thud of that rock hitting Michael. He fell. I called his name, but all I heard was silence. I realized in that moment that I had a performance problem. And the checklist that I just presented to you would be the key for me to get out of that situation. I had to be prepared before I ever got on that mountain. I had to make sure to identify the problem that I had in that very moment, the key problem, so that I could fix it quickly. Somebody's life could depend on it. Now, I hope you never are in a situation like that your life depends on applying the checklist. So why don't we go to an example which talks about a less life-threatening performance problem. Let's talk about JavaScript.
Wait, what happened to Michael?
So I have put together a sample problem that I'd like to talk about throughout the course of this talk. And it is a toy problem that I come up with, but I think it's
I think they say that he will tell us in the end, right? I'm glad that you told us in the end. Okay, so we'll know soon.
representative of some of the things that some of the performance problems that you might face in your own code. And the problem is to compute the 25,000th prime. Pretty simple algorithm here. You start at 1, you count up, and you take each candidate number, and you look at a list of primes that you're maintaining and see if any of those primes can be divided into that candidate number. And if it can, then the candidate number is not prime. If none of the primes, Java code from JavaScript to C++, so it does the same thing.
Wait, what?
And if it can, I wrote some code in C++ and in JavaScript.
All right. Get prime count. What's this? That's a weird code. Function main. Okay. I guess it just wants it to be consistent with C++, right? Yeah, I don't think that's how you write JavaScript code, but fine.
Don't sweat the details of this code. I just wanted to show you that it's about the same amount of code, and I tried to do a pretty good job of porting the code from JavaScript to C++, so it does the same thing. And then what I did is I actually ran the code, I compiled the C++ code to GCC, and ran it. You can see it took about 3 seconds to compute 25,000 prime. Then I took the JavaScript code, and I didn't run it in the browser. What I did is I took the debugging shell that's available as part of the V8 open source code project, and I compiled that and ran the JavaScript with the debugging shell. The debugging shell makes it possible for you to concentrate on JavaScript-specific problems. So for this presentation, I'll refer to the debugging shell in most of my examples. You'll see that when I ran the prime code in JavaScript, it took 15 seconds. So JavaScript's
Alright,
right?
that's slower.
That's not so bad, right? Of course
It's not bad.
Yeah. So
It is?
I just made a big mistake. I told you about this checklist, and I just completely ignored it. I was not prepared. I don't have enough information to make judgment about whether my code is bad or good, whether that number is something I should expect or not. I didn't even try to analyze any potential performance problem.
Okay.
I didn't even get anywhere close to fixing any problem. I'd like to show you how V8 has improved since Chrome came out. This is V8 score on the V8 benchmark, version 7, and you can see that it's got a lot better since we launched Chrome. And we're now at the position where
3 times better.
we can actually make a comparison against the performance of C and C++ code. You can expect to be in the ballpark for certain code. So don't give up here. When you're in the same situation where you say, we're slower than C++, or I'm slower where I want to be, don't just give up. Apply the checklist that I presented to you and see how far you can get. Demand that your application is faster. So, how much faster do you think we can get the JavaScript code? Who here thinks we can do it? We can get it 3.5 times faster.
Me.
All right, we got maybe 5, 10 people. 35 times? Takers? Okay, also a couple of people I know. You know how this game works. 350 times.
What?
One person. The V8 PM. So
I mean, not that much
3,500.
faster.
All right, we got to get at least one brave taker here. So I think most votes were for 35 times. Let's apply the checklist and see how far we can get.
Okay.
Now, I told you the first step was to be prepared. And this means we're going to dive into some technical details of V8 so that you can understand how it works. So fasten your seatbelts. This is where things get a little bit racy. So what does prepared mean for V8? I mentioned this before. You need to
So I guess what he's saying is the code on C++ can be optimized, and so it can be optimized in JavaScript.
understand how V8
Let's see.
optimizes your JavaScript code. You need to understand how V8 actually works so that you can help it optimize your code. Because once you understand how V8 works, then when you actually write your JavaScript code, you can keep those things in mind and make sure that you don't make some of the mistakes that will fool V8. Make sure you learn the tools that are available.
Okay, blah, 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 blah. Let's get us to the actual details.
If you don't have that type of information, it makes it much more difficult. And it's hard to gather this information efficiently and quickly when you're compiling JavaScript, longer than it takes to actually get to doing types at compilation time. And that makes it extremely difficult to get it close to the performance of C++. However, there's some tricks. Hidden classes help make V8 run JavaScript faster.
Oh, here are the hidden classes. Now we know about it.
V8 internally creates hidden classes for objects at runtime, not at compile time. And that's how we get around the problem of compiling upfront, getting the information upfront, because we gather the hidden class information as we go. And here's a key insight, and this is one that we'll repeat throughout the presentation. Objects with the same hidden class can use the same optimized generated code. And that means if you help teach V8 through the way that you structure your code, which object has the same hidden class, you can help it to generate optimized code for those cases. I'd like to show you how this works in a very simple example. So I've got a constructor function here for an object point, and I'm going to instantiate it twice.
All right.
Let's see actually what V8 does behind the scenes. So the first time constructor gets called, V8 creates a new hidden class. So what you see here is on the right-hand side is you see the new point object. The first entry in the point object is a hidden class to an empty point hidden class. And as we assign to the members in point, what V8 does is actually realize you're changing the hidden class by adding a member to it. And we create a new hidden class, and the point object gets assigned to this new hidden class. And if we add another member, in this case y, we get yet another hidden class. And you see what happens here is that not only does V8 create new hidden classes as new members are added, but it keeps track of what had to happen to get from one hidden class to another one. Yeah, so you see we went from empty point object to a point object with an x to a point object with an x and a y.
All right.
And that's important because the second time that we call the point constructor, this hidden class structure is already there. And as the code is executed to add the members x and the members y, you'll see that the object also gets new hidden classes, but it gets the same hidden classes that we created the first time through. So that at the end, we actually have P1 and P2 having the same hidden class. The problem is that if we add a member to P2 that we haven't added to P1 after the fact, outside of the constructor, what happens is that we create yet another hidden class for P2, and it is different from the class for P1. So we're not able to use the same optimized code for both of those objects. So be aware that by doing something like this and creating hidden classes, you're defeating some of the optimizations that V8 can do. I'd like to
Okay.
talk about speed traps to avoid in this presentation. For the most part, all the advice I'm going to give you today is something that is eternal. You can assume that the tips that I give you today you can use forever, except for a couple of cases where I'll say this is something that's temporary, something that we're working
Okay, so
on trying to make better. So let's get to the first speed trap, which is make sure to initialize all members in your constructor function. This comes from the example I just showed you, which is you need to teach V8 which hidden class objects should have after they're constructed, and the way to do that is by putting all of the member initialization in constructor. Always initialize object members in the same order. This follows from that example
that's the thing which we looked at before.
that I gave you. If you add members in different orders, you
Oh, actually, no, not exactly. This is about initialization.
create a different tree of hidden classes, and at the end you'll have objects with two different hidden classes that can't use the same optimized code. Next thing I'd like to talk about are numbers. So
Okay, I
because we
think
don't have
we saw
a lot of
this
type
part,
information in
right?
JavaScript, we have this dilemma. We want to be able to generate code that can handle all possible different values, all different possible types, but you want to be able to have an efficient representation of numbers. And how do we do this? Well, we use a technique called tagging. So inside of V8, we pass around values as 32-bit numbers and objects, but we want to be able to use the same 32 bits to represent both. And that way, we can have one code path that can handle in many cases the objects and integers. Yeah? So what we do is we use the bottom bit
All right.
in each of the values to have a special meaning. If a bit is set, it's an object point. If it's clear, it's what we call small integer or SMI, and that's a 31-bit signed integer. Now, if you have a
Okay, so now we can get back to.
input of a particular hidden class. And what they do is they validate the type assumptions. They get a couple arguments in, they check to see if the hidden classes are as they expect, and if they are, then they know that the code that is in the IC is the optimal code for implementing that operation. If not, something has to happen. A new IC has to be generated that can handle the new type information. And at runtime, if different types are seen than what are expected, then through backpatching, the code is changed to use new specialized code for the new types that are seen. I'll give you an example of how that works. Here's a fragment from the code example.
So this is the code he will optimize soon.
Beginning, the prime number generator. I'd like to take a particular fragment of code there, which takes an element from the primes array and checks whether the candidate number is divisible by that number.
All right, so what can go wrong here? Did he not allocate the array or something? I mean, I don't see anything which is like unoptimized here.
And let's see what the full code generator does with this code. Now, don't sweat the details. I'm going to show some assembly language here. And it's not actually important what the details are here, but I want to show a pattern of what actually goes on here. So each expression generates a little chunk of code here. You'll see that there's a preparation code, and then there's a call out, call to IC to actually do the work. Likewise, for the array element access, there's some preparation work, and then a call out to the IC to do the work. And for the mod, the same thing. And the thing to notice here is that initially, the call is to this initialized version of the IC, because we don't know what the types are going to be. We'll only know that at runtime. This is how it works at runtime. The code on the left here is a small, almost impossible to read version of the code I showed you. And when we're executing this code for the first time, and we get to this IC, the first IC, it calls an internal routine that initializes the IC. It looks at what the arguments are to that operation the first time. It checks the hidden classes. And it says, oh, I know how to do that. I can generate specialized code for that. It does so. And it backpacks.
I have no idea what's going on in this assembly code. I don't think it's worth trying to understand it unless we do a separate stream about it.
You come to the code, it does the same thing again, assuming that the next time you run, you're going to have the same hidden classes, the same types of objects, which is an optimistic but usually valid assumption. It does the same thing for the access of the array element and for the mod operation. And you'll see that each of the ICs, all they are is specialized code that know how to do the specific operation for a given set of object types that are input. This makes a big difference in performance. And this is why you need to understand how some of this stuff works with hidden classes. Because if you get it wrong, you don't actually get the performance improvement that you will see or should see when using ICs and then later the optimized compiler. So if you're running the sample code that I showed at the beginning to generate primes without ICs, you get an execution time of over 600 seconds. When you turn ICs on, you don't have the optimized compiler on yet, it makes a big difference. Right?
Nice.
About 20 times speed improvement. Now, I'd like to introduce a concept that we'll also come back to later. Monomorphic better than polymorphic. Sounds pretty complicated. It isn't really. Monomorphic operations are
That we know already.
operations that always work on objects with the same hidden classes. Right? So the first time you execute an IC, we look at the argument types for the operation, we look at the hidden classes, and we remember them. And if the next time through those hidden classes are the same, it's monomorphic. And if the next time they're the same, it's still monomorphic, and it stays that way. If at any time we see different hidden classes for the arguments in an operation, then it becomes polymorphic. And it turns out that monomorphic operations are easier to optimize. So the code that we generate is better than for polymorphic operations. So here's an example. Let's say we have a function add that adds two things. And if I call that with two integers,
Alright, this is monomorphic.
it's monomorphic. However, if I call it again with two string arguments, I use the same operation, this plus operation, to work both on integers and on speed
Yeah,
tracking voices,
that
wherever
we
possible.
understand.
Don't monomorphic code to polymorphic code, wherever you can. I'd like to talk about the optimizing compiler. We talked about the full compiler generates pretty good code, gets executing as fast as possible. The optimizing compiler comes back later with the code that's really hot and recompiles hot functions. Why does it do this? Well, we've gathered information about the types of the objects that we're operating on through the ICs. And the optimizing compiler can take that information and make decisions about how to optimize the code better. What happens is the optimizing compiler takes that type of information from the ICs and speculatively inlines a version of the operation based on history, what it's seen before in the ICs. And it also means that it can inline function calls that are monomorphic. This includes constructors. This is actually an input feature that we've added recently. By enabling inlining,
Operations speculatively get inlined. Monomorphic functions and constructors can be inlined entirely. Oh, okay. So they inline this type specific thing, I guess.
inlining these operations in the optimized code, other optimizations become possible, and that's what the optimizing compiler will actually do. We'll go over this inline code and find more opportunities to make it faster. Let's see how that works. Again, the warning, here's assembly code. It's a very similar process to the full code generator.
All right. So CMP, I guess, is compare. MOV, yeah, I don't know.
Generate a little piece
I
of
don't know
code
what's going on.
But this time, you'll notice, as we generate each piece of code, there's no call at the end. And in fact, when we're done, it's straight line code. So let's compare performance using the optimizing compiler to the two runs that we did before. You'll see that with the optimizing compiler, we're even faster. We're about 50 times faster than the original code.
Nice.
One thing that's really useful is actually to find out which functions are being optimized by the optimizing compiler in V8. So there's an option you can pass to the DHL. That'll do just that. It'll output the information about which functions get optimized. However, there are certain circumstances in which the optimized compiler can't optimize a function. This is called bailing out. That's what we call it, bailing out. And the reason is there are certain language features that are just not supported yet by the optimizing compiler. The most obvious example is try catch. So if you have a function that contains a try catch block, the optimizing compiler right now can't optimize that. We hope to change that in the future. But until then, there's a workaround. If you have performance-sensitive code that you'd like to call from or access from a try catch block, wrap it in its own function. Here's an example. We have a function that's performance-sensitive. We call that from the try piece, the try catch block in another function. And by doing that, it allows the optimized compiler to optimize the performance-sensitive function, even though it can't optimize the try catch block.
Right.
If you want to find out which routines cannot be optimized by the optimizing compiler and why, there's an option you can pass to the debugging shell called trace bailout, and that'll actually tell you the functions that could not be compiled and why.
Nice.
The last thing I'd like to talk about is de-optimization. So the optimizing compiler is pretty good at generating code, but there's a catch. The optimizations that it does are speculative. It makes the optimistic assumption that what it has seen in the past is going to be just like what it's going to see in the future. And that usually pays off because usually your code keeps running like it has before. However, as with all optimistic assumptions, that may not be the case. So when you're driving down the Autobahn in Germany and you're doing 200 kilometers an hour, sometimes you're working under the optimistic assumption that you're not going to be caught going over the speed limit. Remember I told you there are some stretches of the Autobahn with the speed limit. And you'll see out of the corner of your eye a red flash from two of these things on the side of the road. And you've just been caught in a speed trap. Because your optimistic assumption that you were not going to be caught speeding was wrong. And what do? You slam on the brakes, you slow down to the speed limit, and you probably drive that way for a while. Yeah, slower. There's a similar process that happens in optimized code in V8. Invalid assumptions lead to the optimization. When one of the assumptions is no longer true, when one of the hidden classes that you get for an argument to an operation is not what you expected, then the specialized code we generated is no longer valid in the full compiler code. So we can continue execution, but now it's at a slower speed because we're using the version of code that is good but not great. And a reoptimization of the function might happen. And what that means is I'm running your code. Right? If you have object types that you run in optimized code, and V8 uses to optimize that code, and then you later introduce new types, that optimized code will de-optimize. And if you do that too often, it has a cost. You can tell the debugging shell to output the routines, the functions that it de-optimizes on by passing the trace de-op option to the debug shell, and it'll output which ones it de-optimized on and why.
So I guess this is what this thing does. How's it called? The de-opticate. I think it just runs V8 with all those things, all those flags, and just shows the UI.
Now, most of you are doing web development, I assume, and therefore you probably want to be able to look at your code in Chrome as well as directly in the DHL. You can pass these options.
Oh, that's cool. I didn't know you
also
could do
directly
that.
using the JS flags option, and the output will all show up in standard out when running Chrome. Okay, so that was the be prepared part. You now understand a little bit about how V8 works. Let's talk now about identifying and understanding problems using that knowledge. What does that mean for V8? First of all, ensure the problem that you're looking at is a JavaScript problem. And this is sometimes a little bit tricky. You can use the dev tools in Chrome to figure out where you're spending time in your web application. It may look like JavaScript, but be careful. It might be the case that there's also DOM interaction. So a really good way to do that is if you can take that code that you think is a performance bottleneck, pull it out and run it in the DHL. That means it's pure JavaScript because the V8 project is just JavaScript. It doesn't have, it's integrated in Chrome, but in itself, it is just the JavaScript execution environment. So if you can take that code and run it with the DHL, then you can analyze the problem as a JavaScript only performance problem. Collect metrics, measure where you're spending the time in the code, and then look at bottlenecks and fix them. So remember the example that we had at the beginning. Prime numbers.
Yes.
If you run it in the shell and pass an additional argument, the dash prof argument,
Okay.
it will run the program while also sampling the execution profile. And it'll write a log that you can then analyze with another tool to see where you're spending your time. Before we look at that output, where we're spending the time, I'd like to go over briefly again where we're spending the time, or what we're doing in the program. There's a couple important functions here in the prime generator. First, we add prime. There's a function add prime to the existing list. There's a function that actually tests whether candidate number is.
Oh, so when in the add prime, they do not. Yeah, I don't know if this primes array was allocated. Maybe that's a potential route for optimization. But it's not sparse, right? I'm not sure how many primes were there. But they're like 65,000, like you said, or no, or less. I think less. Otherwise, I don't see anything. Oh, but if you allocate this in advance, then it won't work because it iterates over them, right?
Visible, or it's visible one of
Why wouldn't they just use push? Would it be more performant? I have no idea.
one of the existing primes. And then there's the main routine, which does the high-level algorithm. It starts at 1, goes
Uh-huh,
checks whether it's
25,000.
visible by an existing prime. If not, it adds it to the prime list. Otherwise, it goes to the next one. So what's our expectation? The prediction is that we're going to spend most of the time in main. And the reason for that is all properties and functions are monomorphic. I wrote the code to be that way. All numeric operations are smize. We do a pretty good job at optimizing those. All the functions could be inlined. And then none of the optimizations are failed. So my expectation is V8 is going to do a really good job of optimizing this code. Okay, so let's take a look at the output and see where we were spending our time. So this is the output of a tick processor. It takes this
Right.
output log that's written with performance data and prints it in a free format. You see there's two sections of the output here. I've actually abridged this. It's much longer, but these are the important parts for our profile here. There's a JavaScript section. This is the time we're spending in generated code. This is JavaScript code executing in either the full compiler code or optimized code. And then there's the C++ section, which is it's often the case you'll have C++ symbols in the profile because there's some operations that we can't do in generated code, so we have to call out. And as expected, we spend a lot of time in main, but it's actually about 25%. You see there's three columns here. You see how many ticks you're spending in in that routine in this function. You'll see what the percentage is of the overall execution time. But in this case, it's only 25%. That's weird because I expected a lot more. V8 should do a really good job in this code. If you look at the other items that show up in this profile, this is weird. We're spending time doing a binary op stub with an oddball. Remember I told you those things like true and undefined? No, we don't have that in our code. That's kind of strange. And we're spending a lot of time in library code doing modulo.
Okay.
That's kind of strange. We should be able to inline that as well. I didn't expect that. And then here's another one that's kind of weird. We're doing a conversion from a number, extracting, or taking a number and boxing it. And we really should be.
Wait, this is C++ code of in the JavaScript code?
Generating very good code for this program. We're spending way too much time.
Oh yeah, they have this number from double, but why would they have doubles
Not
there?
executing the JavaScript. We're calling out to libraries. Something is very wrong with this code.
Yes.
So can you spot the bug? The hint is that our array is only of length prime count, and we've actually exceeded the end of the array in our calculations.
Oh. Oh, so it will get undefined at some point, right?
And in both the C++ and JavaScript version, it doesn't make a difference in the results. And this is the thing that you gotta watch out for, is that even though you don't see that there's a problem in the results, the program's a lot slower than it needs to be. So let's fix that. Let's actually not do an out-of-bounds array access. And we'll rerun the profile with the fix, and you'll see this time, this is what we were expecting. That small change now makes us generate much better code, because we're not accessing outside of the array, getting an undefined object, this oddball that we're trying to do math on. And now we're spending 99% of our time in main. This is what we expect. So let's see actually what this makes, how big a difference it makes on the profile. When we run the code against the C++ code again, look at that. C++ code, 3 seconds. JavaScript, 1.8 seconds. We're 60% faster.
1 point. Oh, nice.
Well, I forgot to optimize the C++ code.
Okay.
So when you do that, C++ is still faster, but it's 17% faster. It's ballpark. Have to take all this with a grain of salt. I chose an example where I knew V8 would do a pretty darn good job. More and more, we're optimizing more cases that makes V8 faster in more situations. So I expect in the future we'll get closer and closer. But my point here is that you need to make sure to take a look at, to spend the time optimizing the code, to know where you're spending your time, because you can actually make your code very fast. So fix what matters. We did a lot of time analyzing our existing profile, tweaking it, knowing how.
That's a good talk. So basically, just by having like one character and having off by one, the whole thing went like 6 times slower.
V8 works. The last thing I'd like to point out is make sure you don't forget to optimize your algorithm. So I have a new version of the program here where instead of iterating over all the prime numbers, I only iterate through the square root of the candidate, which is sufficient to actually test for whether it can be divided by one of the prime numbers. And if I run that result, if I run that in the time that, then you'll see that now I'm under 500th of a second. And if we compare that with the original version, which was 15 seconds, it's 350 times speed up.
Yay.
So, in summary, keep your eyes on the road, be prepared, learn a little bit about how V8 works. Identify and understand the crux of your problem, and fix the thing that matters. You don't have a lot of time to do performance optimization. Make sure that every minute counts.
So what happened to Michael?
He had taught me how to tie a special knot, which freed my hands while he was hanging. I was able to call on my cell phone the mountain rescue. Michael regained consciousness, and I could lower him down. The helicopter came and took us off the mountain. So,
That's
even though he had
cool.
broken ribs, he's fine. Thank you.
Oh, I want to come back because I saw a comment from Vyacheslav Yegorov, whose article we've been reading. JavaScript agents share some design decisions, so most of them suffer from the same things. If you try this example in Firefox or Safari, you will see that performance improves there as well. In C++, you can read out of bounds. Whether you get an error or not depends only on the memory layout. In this particular case, you never actually read out of bounds, you just read an uninitialized part of array. And C++ actually does the same. Okay, that's not very helpful. Cool. So I guess this is kind of inspired by this talk. I guess it's a summary, right? Most of the objects in heap are 4 bytes, byte aligned. According to spec, all numbers are 60-bit floating doubles, but that's not what the dude said. Maybe this is newer. V8 passes around 3-bit numbers to represent all values for improved efficiency. Ah, okay. Bottom bit reserved as tag to signify if a value is small integer or a pointer to an object. Ah, I see. So I guess it's technically 63-bit, right? Okay, what about this thing? Oh, it's the same. Right, it's the same. Be prepared numbers, it says.
This follows from that example.
Oh, it's the same talk.
If you add members in
Okay. Numbers bigger than 31 bits. Oh, I see. I see. So it's either 31 or 64. This makes sense. Stored inside an object referenced via a pointer. Extra overhead. Blah, blah, blah. Cool. Okay, I think we figured out the numbers part. Now the objects part. This is not a very useful diagram. So it seems like it says for simple properties, but what are simple properties? Most above all blocks have a map property describing their structure. Named properties are stored in Overflow Array. Why would they not fit? Maybe it will say later. Okay, can read. Ah, here you go. This is also 2012. Ah, here's the same thing. Most objects contain... Ah, so this is... When was this updated last? 2018. Yeah, I don't understand. Most objects contain all their properties in a single block of memory. All blocks of memory have a pointer to a map which describes their structure. Named properties that don't fit in an object are usually stored in an overflow array. But why? Numbered properties are stored separately, usually in contiguous way. The diagram only... Blah, blah, blah. Alright. V8 has its work cut out. The JavaScript standard allows developers to define objects in a very flexible way, and it's hard to come up with an efficient representation that works for everything. Yes. An object is essentially a collection of properties, basically key value pairs. You can access properties using two different kinds of expressions. True. According to the spec, property names are always strings. And then it gets converted. Arrays are just objects with magical length property, and most properties in arrays tend to be named after non-negative integers. Length returns the largest integer name plus 1. Alright. Fine. Since JavaScript object is basically a map from strings to values, why not just represent them with hash tables? This works fine, and V8 actually uses hash tables to represent different objects, which the optimized representations detailed below don't work for. However, accessing a hash table is much slower than accessing a field at a known offset, of course. Let's talk about how strings and hash tables work in V8. There are many different ways to represent a string, but the most common for property names is a flat ASCII string, where all characters are stored contiguously. How do I even pronounce that? Near, touching, bordering, neighboring, besides, adjacent. With 1 byte per character. Strings are immutable. Yeah. So I don't understand this thing. What's this numbers? Strings which are used to access properties are symbols, which means they are unified. If a non-symbol string is used to access a property, it's unified first. Hash tables in V8 are large arrays containing keys and values. Initially, all keys and values in a hash table are undefined. When a key value pair is inserted, the key hash code is computed, and the low bits of hash code are used as initial insertion index. Okay. If there is already a key at that index, the hash table attempts to insert into the next index, modulo length, and so on. Here are pseudocode. Okay, that's like standard hash table. Some symbol strings are unique, and hash codes for strings are computed at most once, so they cache it. Computing the hash code and comparing keys are fast operations in the common keys. However, this is still not trivial, and executing them is slow. So V8 will try to optimize it and do it in a different way. Oh, here you go. Oh, that's even older. That's even older.
Hi, I'm Lars Bach. I'm the tech
Hi,
lead
Lars.
for the V8 project. And the V8 project is a new, exciting, high-performance JavaScript engine.
Oh, this is from like the original intro about
We use here
V8.
at Google.
Okay, we're not gonna look here, we'll just read the article. Oh, this is the example which we saw in the video, right? Using maps as a table of that's interesting. Table of descriptors with one entry for each property. Map contain other information as well, like the size of the objects and pointers to constructors and prototypes. One entry for each property. Okay. Objects of the same structure will usually share the same map. Cool, so we have a map, have object of a size 20, I guess, bytes. And then we have field X and Y, and each of them takes 4 bytes. Okay. Special descriptors called transitions. When adding a new property, we want to create a new map for the object if we don't have to. We'd rather use an existing map. Transition descriptors point to these other maps. Okay. What if a new property is... So this is still from that talk, right? In that property has never assigned before, create an M3. What if properties are assigned in different... Okay. You might be wondering how it knows how much memory to reserve for an object. Obviously we don't want... Yeah, that's interesting. To reallocate objects every time a new property is added. We also don't want to reserve a big chunk of memory for tiny objects. V8 uses a progress called in-object slack tracking. Okay, initially objects allocated by a constructor are given a generous amount of memory, enough for 32 fast properties stored within the object. Once a certain number of objects has been allocated from the same constructor, last time this person checked it was 8, V8 checks the maximum size of these initial objects by traversing transition tree from the initial map. New objects are allocated with exactly enough memory to store this maximum number of properties. The initial objects are also resized using a clever trick. Okay, when the initial objects are first allocated, their fields are initialized sized such that they appear to the garbage collector to be free space. The garbage collector doesn't actually treat them as free space, since the map specifies the size of objects. However, when the slug tracking process ends, the new instance size is written to maps in the transition tree. So objects with those maps effectively become smaller. I don't understand this. Since the unused fields already look like free space, the initial objects don't need to be modified. Since the unused fields already look... Oh, okay. What happens when a new property is added after in-object blah, blah, blah complete? This is handled by allocating an overflow array to store extra properties. The overflow array can always be reallocated with a larger size as new properties are added. I guess that's what they're showing. So they have space for some properties, and then there is overflow array. There's also fixed array. JavaScript does not have classes, which means method calls work very differently than in C++ or Java. Methods are just regular old properties. Okay. Okay. Yeah, so here... Another transition can only be followed to a map with a constant function descriptor, as long as the function being assigned is the same as one in the descriptor. Transition. Alright, so it has to be like the same function, right? Distance. Okay, so we're looking at this example, so it has to be the same function, right? So if programmer reassigns the point distance variable to different value, the transition won't work anymore, and we'll have to create a new map. Note that you don't generally load constant functions directly out of a map, like we do with vtables. What's vtables? I have no idea. Instead, optimized JavaScript code checks whether an object has a particular map, and if it does, we know it has a particular constant function. A pointer to function is embedded directly in optimized code. Okay. JavaScript provides another way to work around the problem of shared properties. Every constructor has a prototype object associated with it, yes. Instances of a constructor behave as if they have all properties contained by their prototypes. Our example could be written as follows. Oh yeah, so I'll put it on the prototype. This is extremely common. It's also the canonical way to implement inheritance, since each prototype object may have its own prototype objects. I don't know how it's stored. Okay, and the last thing is the numbered properties, right? If they are sparse enough. For instances, the same, blah, blah, blah. So separately, they start that makes sense, because you can quickly get them. Maps don't contain descriptors. Yeah, this concept of map is still I still don't fully understand it. Most commonly, objects have fast elements, which means that elements are stored in contiguous way. There are 3 different fast element kinds. I didn't know that. For small integers, for doubles, and fast values. For doubles? Okay. According to the spec, all numbers in JavaScript are doubles. Frequently work with integers, though. JavaScript doesn't provide any way to specify how many elements an object will contain. You can say new array 100, but this only works for array objects. If you store a value to an index which doesn't exist, V8 will reallocate the elements array and copy the old elements to the larger block of memory. V8 can handle arrays with holes, elements as so you get an undefined value. Okay. Of course, there are limits to what you can do with fast elements. If you assign to an index that's way past the end of V8 will downgrade it to dictionary mode, right? Okay, I think that's fine. Who's jcon prod? Go. Interesting. So the Russian person switched to Dart, and this person switched to Go. Like all the people who are writing about V8 optimizations. This is still not very clear. Like, I think I understand a bunch of different parts, but I don't understand how they all come together. There should be like a talk, kind of like what that dude did with the 4 items, but with like 50 items or something. Anyway, I think I'm good for today. We did not create a pull request, but that's probably fine. We did fix this. Let me verify that. It's in emergible state. Forbidden labels detection. Your tests failed on Circle CI. Let's see. No, Angular will not become fast. Unfortunately, yes, we'll have to let it be. Okay, so I think we just need a newer version of this thing, right? So I'll just git. Oh, maybe now is a good time to figure out the change list. So I'll create a new change list, and I say perf stuff. Okay. I would expect this thing to go out. I would expect all those things to be done. Set active change list. No, I'm so confused how this works. I always use create quick change list button. The empty change list is no longer active. Do you want to remove it? So there should be a create quick change list button. Change lists. Shelf silently. Okay, I can use shelf silently, I guess, for now. Up. Okay. Okay. Terminal. Git branch. Where am I? Okay, I'm on the right thing. So I gonna pull git pull, I think. Nice. And then I can do there was a pull merge reset head push. Rebase my GitHub fork from upstream. Could not commit stage. Oh, what? Why do I have stage changes? Git diff. Oh, it just git rebase abort git diff. Isn't it deleted? Okay. Git status. Your branch is up to date. Okay, let me try it again. I don't know what's happening here. Maybe I can do rebase my git fork upstream. Okay. Could not commit stage changes. What does it even mean? Git status. Improve next commands to your rebase. Open git panel which has a console. Okay, console. Here you go. Could not find module EJS. What's going on here? I didn't know there was a console in Git. That's something I learned today. Path spec lol.js. But didn't I thought I shelved it so it doesn't have to do all this stuff. Okay. Yeah, so this file doesn't even exist, right? Okay. So you're saying it's an old mess. Maybe I can just clear the whole thing and just do it again. Terminal. Git rebase abort. And now I'll do it for the third time. Yet again. Rebase upstream. And now I can... Maybe I can just click on something and it will bring me there. Nope. Okay. Cannot find module EJS. I can do it from... That's fine. Okay. So this is Husky trying to do something. I think I can just go continue, right? Module not found. Dev infra. ngdev. dev log git status. Oh, is it because just amend that? What's this? Base support. Fetch upstream. Git rebase upstream master. Let's see if I can do it through the terminal. Oh, it's the same, right? I'm not helping IDE by doing shit from the console. No, it's the same message. It's the same error. Module not found. Like we get the same error. I think I would rather do it from the console just to make sure that it's not IDE. Like I would rather not even use any of the IDE stuff. So I assume this is run on like on commit, right? Maybe I just need to do like npm install. Oh, yarn, right? I think we just don't have some module needed. Oh, yeah. Okay, let's see if this works. But that's weird. So they do have pre-commit something which does not work. But it stopped working in the middle of the rebase. No, I think what happens is, so we are rebasing on top of master. So it gets the master and that gets my first commit. So it starts committing or doing like whatever it's supposed to. So pre-commit hook is run. And then what it does, it gets some EJ, that's my guess, right? It has a new thing, which it, yesterday somebody added this EJS import. So we cannot, so it fails, right? Because we don't have this specific module. And now it works. Successfully rebased. This is a very interesting problem. Okay, so I'm gonna push pish git pish. Is it a thing? Okay, no. Git push force with these. So I guess everybody will get that error then, right? Everybody who's rebasing in the middle of this thing, and everybody will be like very confused. Cool. Let's verify that we have the right thing. Oops, I accidentally closed the chat. Coming back. Yeah, so they need the hook on pull, which does yarn install, but then it will be too slow, no? Let's see. It's so if I do yarn install again, how long would that be? That's not slow. It's not bad. Let's see how they do hooks. Package JSON. Is it Husky? Husky hooks. No. Commit. No. So it has Husky, but I guess there is like a separate file or something, right? You have a team which does that because developers are not great friends with pre-commit. Okay, no, not here. Husky. Here. Pre-commit. I don't know what this is. So it's this Husky sh. Okay. Okay, let me verify that my rebase didn't break anything. Uh-oh. Uh-oh. That's not good. I think it lost the file somewhere, right? Or maybe, oh, never mind. They're back. They're back. Yeah, I don't know if it would be an overkill. Okay. And whatever GitHub doesn't have a fix up. Is not a fix up. All right, yeah, we talked about that. Which it should be. Right, so it seems like this part is good. Let's see if they have anything Husky related with array options. I don't remember which hook. I would assume it's on pull, right? Can you have a git pull hook? Prepare commit MSG. Check Husky. Oh, if it has the hook. I saw like people being like mad at Husky because they did something with the license. Why Husky has dropped conventional JS config. Okay, I want to read that, but I think I also should go do something else with my life. Husky improves commit usage. Husky install. Everybody in your company suffers from GPL license. Tell me more. What I don't know much about licenses. I know there is like Apache and MIT, which are good ones, and like the rest, I have no idea. Docs. Here documentations. Zero dependencies, lightweight, powered, npm yarn, used by all those wonderful companies, articles. Alright, I want to know. Even NGCLI has some GPL dependencies. So what's wrong with GPL? And screws up your report when scanning. I thought it's good, no? Public GNU. It's not because of Stallman, right? If you modify GPL code, you have to share it. I see. Yes, I can see. That might be hard. Yes, that sucks. Yeah. And I don't think you're even planning to change a GCLI at any point. Right? Yes, and also you don't ship it. So I think you have to like split your report in like dev dependencies report and like whatever goes in the bundle report. Or maybe you can like how when you generate the bundle, all those licenses go in. So maybe figure out how to analyze this bundle or something. Yes, okay, GCC is also GPL. I assume you use GCC, right? They found a production flag for these tools. Source clear. Nice. Gonna try it tomorrow. Makes sense. Okay. Hooks. Blah, blah, blah. Yeah, that sounds like an overkill. Yeah, it's funny like how like they just wake up at one day and like, oh shit, by the way, I think we should should fix all of it. Alright. So I guess the Husky has a new format. I don't care. Okay, so which hooks exist? Git hooks. In Google, they do not use ngCli to build things, no. They do use ngCli to generate stuff, but they build it with like they have their own pipeline. Pre-commit. There is pre-rebase hook. Yeah, but you're right. We cannot do it on push. We cannot do it on rebase. Maybe you can do it pre-commit. 1 second. Yeah, I don't think. I think. But then on every commit, it will do yarn install, which will be awkward. Maybe there is like some kind of yarn verify or something. Also, seems like all the GPL license packages have double license. What does it mean? Oh, GPL or MIT. How is it possible? But that's fine, right? If it's or, then you can just pick whatever you want. Or no? I don't know. Check NodeForge. Or Fraction.js. License. Under the same license, locally used under the terms of either BSD or... That's weird. License compatibility. To minimize license proliferation, and individuals argued compatibility with the widely used GPL is an important feature. Especially... Yeah, so BSD is like the nice one, right? Not a regional fork clause. RGPL compatibility is that they're without conflict, and the new combination have the GPL applied to the whole. Okay. Oh. That stuff is complicated. It's like... not even compatibility, I think, like... And... why? Comparing. Hey, no, I'm not going there. I'm not going there. I should I should go do something else. All right, let me verify that. You're also looking at Fraction.js, MIT, or GPL2, or later. MIT or GPL stuff. But if it's or, then it's fine, right? And you don't have to open source your changes if you're using GPL. You could modify it and use it for your own purpose, as long as you're not distributing it. Right. By the way, Husky starting from v5 is free only for non-commercial usage. I think it means distributing it as open source, not the builds. Oh, I guess you still ship it, right? Yes. Okay. Yeah, that's what I was talking about Husky, but I think they were like, we'll try it and then we'll change it back, and I think they came back to like the normal free license or whatever. Can I do... okay. Let me take it off the screen and then look up Husky license, and then I can bring it back. I just want to say there will be like no posts from Sitnik, and then like the first post is from Sitnik. Cool. So here is Sitnik saying like you should not use Husky, you should use the other thing. Yeah, temporarily dropped open source license, but now there is Husky 6, which I think brought it back. Yeah, this is not a very useful source. Okay, stop here. Just stop doing what I'm doing. Go back to notifications. Right. I have to verify. Wait, what happened? Why are they not found again? Head back to the latest changes. This is weird. I guess it's GitHub being weird. Okay, everything is broken now. All of it is broken. Let's see. Four tests failed. Oh. Yeah, because I didn't change codes everywhere, right? Ivy. Hi.
Say hi, Papa T.
Hi. T. From Karma. There's like, I think it said web somewhere. Let me try this. So I think because I changed codes in one place, I have to change them everywhere now. Which kind of makes sense. Let's see. So this is what I want to change. Like this, like this. So basically all the codes go away. That's good, that's good, that's good. Yeah, I think that's good. Expected synthetic. And I have to do the same here. Wait, so what's happening here? So what did I just fix? Server render. So like this. I can just do. Nice. I think that should pass the test. I'm not gonna push until it passes the test. What's this stuff? What's this? I have no idea. Maybe Dan knows what this stuff is. I'll just can I revert them? Roll back. Roll back. Committer of the amended commit differs from default. Oh, got it. Because I should not amend this. Somebody else's commit. And then Husky 6 returned to MIT. Yeah, so this was like a weird thing, and I think they lost some users because of it. Which I don't necessarily think it was a bad idea. But I think they could have done it more gracefully. So fix up, fix codes. Oh, no, not like this. Improve error message, fix codes. Like this. So I'm gonna commit and wait until it builds all of it. So we're gonna check out Husky. After being happy to announce Husky is MIT again. Commit. So basically they were like, give us money, which kind of makes sense. What's JSON placeholder? Free fake API for testing and prototyping. Oh, that's cool. Oh, nice. So they do get some monies. All right, what's happening here? Oh, it's still committing. Maybe it cannot commit without Blaze or something. All right, anyway, I think I'm just gonna finish this off stream. I have 1 hour left of my free life for today, so I'll go chill in the park a little bit. But yeah, good seeing you, Dan and Jorginho. And Dan, good luck with the licenses. I hope it will get resolved in some nice way. Yes, alright. Cool. And then I'll probably start streaming a bit more. I had like few busy weeks. But we'll see how it goes. Cool. See everybody later. Bye.